Yes. Yeah, if you can introduce them.
Hey, good morning, everyone. It is my great pleasure to introduce to you Dr. Zikui Liu. Zikui is the Dorothy Pate Onright Professor of Material Science and Engineering at Penn State. Zikui received his PhD from KTH in Sweden, and he has been at Penn State since 1999. I believe the reason is obvious. Penn State has one of the best MSc program in the nation. Zikui works at the frontier of first principles calculation, data science, and machine learning, and integrate them and apply them to solve thermodynamic, kinetic, mechanical problems, and especially the calculation of phase diagrams and material design discovery. And Zikui is the author of more than 500 publications. Zikui is the recipient of a long list of awards, including the Hume-Rothery Award. And that TMS was actually held here in Phoenix, and I was among the speakers to celebrate it with you. And the Gibbs Phase Equilibrium Award. And also Zikui was elected as a TMS Fellow this year. Congratulations. And Zikui is president of the ASM International. He's on the board of the ASM Board of Trustees and the TMS Board of Directors. And 20 years ago, Zikui created a term of materials genome, and this has connected material science to data science and create a new direction of research. So with this, the floor is yours.
Thank you very much, Qijun. And I still remember about 20 years ago, Qijun's advisor, actually, and I met at one of the meetings. And I really admired his work. I asked him to write a paper about his program. And the paper is one of his top citations today. That was about 20 years ago. All right, that's fantastic. Well, I want to thank Krishna and Kumar giving me the opportunity to present our work here about Zentropy. So I believe I shared the screen already. So what I'm going to do is I just go to the screen. I need to close this one. I assume everybody can see my screen. I'm going to start. Right. So my title, right? The title email to everybody was a bit longer, so I'll make it shorter. I got a Zentropy. My name is Zikui Liu. I'm from Pennsylvania State University. This is our group website in case you would like to browse to see what we have there. Okay, I started with my talk with Einstein's famous quote. And back in the 1920s, he said, God does not play dice with the universe. So what he really meant at that time was God, he's not about religion at that time. So God is not a religion God. What it really means is that he's not comfortable with quantum mechanics. Okay, because quantum mechanics says it's uncertain. Einstein thought the universe should be certain, and that God will not play dice randomly with us, with the nature. However, you may know that quantum information was just got the 3 people got Nobel Prize in physics this year, just they announced this week, and it's about quantum. Okay, so quantum is real. It affects what we do. So just to emphasize that how history changes, right? 100 years before, not so many people believed quantum, but today quantum becomes part of our a core component of our science. So if you look at this question, this comment by the quote by Einstein, God does not play dice. What does it mean, right? You think of this one, they actually have a few keywords from this statement. One is God. So what is God, right? It's of course we know that if you, whether it exists or not is for debating, but we know it's nature about science from our point of view. And in play is basically when you play something, you need to have time, you need to have kinetics. You need everything happens. You must have a barrier, so have a kinetics. And then dice basically is what you see, right? What observation is experiments. So dice is the outcome of our observations. The universe is basically a system which you study. So it's thermodynamics because thermodynamics defines system. Now you put what Einstein said at that time. It's really that we study science, we do thermodynamics, we do kinetics, we do experiments. Okay, so that's basically the idea. It's really the theme which I'm trying to present today. I know that there are many students here. I hope this can inspire students to think broadly about science as a materials, as one of the key components of science. Okay, so the question is that if God does play dice, what dice would it be used, and how it will be played? So that's the question. So let's keep that question in mind and see how it evolves. Okay, I don't know how many of you have seen this bird cage, some MateriAlZ. It's about configurations, right? So this is a piece of paper, and this paper has two sides. We know that one side is a cage, another side, and it played. No, it doesn't play. Just 1 second. It doesn't want me to go there. Okay, let's go here. That's okay too. Oh, you get some questions. Get some. That's not good.
Why is the pillow square?
Sorry about that.
That you asked. This is J, the inventor of the
Let me
pillow
see
cube.
this one.
This is a
Here. All right. So if you stop this play, you see that is a cage, right? If you play with it, oops. Let's go to the beginning. Go to the beginning. Go to the beginning here. You see that it one side is a cage.
Zico, we don't see the movie.
Oh, don't see the movie.
Working. No.
Let me just, let me do that. Let me just reshare it.
Yeah.
Let me just reshare it. Let me just reshare it. Yeah. It played yesterday well, but it didn't look like it did not play today.
Sometimes if you use the pointer in Word, it doesn't, sometimes it causes trouble. In Microsoft, I mean, yeah.
Let me just replay, reshare the screen. That will work. I know that. Okay, if you share the screen, I share the whole screen instead of just PowerPoint presentation. There is you're going to play. And when you share it, oh yes, let me do another resharing. Sharing here, it has share the sound. Okay, share the sound too. I mean, share sound. You can hear the computer sound too. All right.
Well, we heard the sound. We heard the music.
You heard the music.
Oh,
huh?
okay.
All right. Oh, well, it's about this one. It's about this one. Let me try it again. Now you see the.
No, don't. I would.
Oh, no, it's
yeah. Maybe it's good now. Try now.
Yeah. Now play.
Yeah, that's working. Yeah.
Now you see the bird, right? Now, and so you see the cage and the bird. That's clear, right? Okay. Now you see that's a bird, and if you go back, it's a cage. So a bird, a cage, right? So you clear that this has two sides. Okay, one's a cage, one's a bird. However, if you play it, you put it slowly. You put it slowly. The question is that we know if you do very slow, you know it's two sides, they're different. But you play fast, the bird in the cage. So what does it mean? Does it mean your observation is wrong? It's illusion, or it's reality? So that's very, very interesting. But you do experiments, right? So you do experiments. So you do experiments, if you spin it very slowly, you see the bird in the cage separately. If you spin fast enough, you see the bird in the cage. So both observations are right. That's what you observe. Okay. So that's actually what happened. That's what happened in science. But before I go to science, I want to talk about how important material science is. Materials is closely Is everything okay now? Everything good?
Yeah, it's good. Yeah, we're good. Yeah.
Okay, so if you talk about materials, we know that if you look about history, we have the Stone Age, that's the natural materials. We have human-made materials. We get bronze. It's very interesting. Bronze is 12% of tin. You ask why is it 12% tin, right? Why is it 12%, not 11%, not 10%, for example. And then we get the Iron Age. Okay, now then we have the Industrial Revolution. We got the steam power, electricity, and the computerization. And then now we're in the materials industry 4.0 is digitization. Okay. So now if you look at the history about digitization, particularly for in terms of knowledge, you can have, you can make stuff, right? Talk about the materials. So the materials, when you make materials, really you're trying to make the materials certain shape, okay? And then you're going to control the properties. But the properties we know is controlled by the phases you have. Right? So it's really fundamental here. Is you have to understand the property of the phases. So how do we understand the property of the phases? Well, we know that's thermodynamics, that's phase stability. If you look at the history of thermodynamics, of course, it goes back a long time ago, but the system, it was systemized by Gibbs in 1870s, like 150 years ago. And then 100 years later was digitized by Kaufman. That's in terms of CAFAD modeling he developed in the 1970s. And 50 years later today, and we are talking about the material design now, a lot of them, most of them actually use CAFAD as a base database behind it. So we'll talk about next 50 years or that. So I will give one slide about CAFAD modeling. It basically models a free energy function. You typically Gibbs energy function. We usually know function temperature, pressure, and composition. But I also want to talk about the internal degree of freedom. Okay. And today I was talking with Peter and Krishna in the morning that the pressure maybe should use stress, right? Because for solid phase, stress is very important. When this kind of modeling, we started with the quantity we measure. We measure the derivatives of Gibbs energy with the heat capacity, second derivative, entropy, first derivative, and activity it's also first derivative to the chemical potential. And they also measure the phase equilibrium data. They put them together, develop a Gibbs energy. The question is why this is not enough, right? Because this has a large uncertainty. So you need this one to make the data much, much more accurate. So it can predict the phase transformation much, much accurate compared with the experiment. To that database, you start with the pure elements. You do the binary. We have like 70 some pure elements, which we use. You have the binary system, internal system, a lot of more and more systems get multi-component. So basically, Kaufman developed this kind of a mechanism to go through that. After you get a free energy, then you can do the material design. Okay, you can do equilibrium, because sometimes you want equilibrium high temperature. You can talk about driving force. You want to control driving force in nucleation. Then you can talk about the properties too, right? The physical properties, chemical, a lot of them are first and second derivatives of the free energy. We don't have time to talk about them, but I do have a couple of tables to show that how the typical properties we measure are related to the derivatives of the free energy function. And now you can see that that's where I came up with the material genome concept back 20 years ago. The idea when I started as a faculty at the Penn State, I was thinking, you know, we got to do something new, right? I always do that. So at that time, you probably know that the Human Genome Project was very successful. You know, it was close to the end of that big $1 billion project. And CAFAD was very successful too. It takes individual phases as a building blocks. So then I thought maybe we should have material genome. Okay. Of course, this you cannot just invent it, right? You have got why you got some inspiration. So we got a kind of few interesting projects from NSF and NASA at that time. We got an education program to talk about thermodynamics, kinetics. Okay. Then we worked on the nickel-based superalloy. Then we talked about the ITI's information technology research. So that was actually, if you go back to data science, I think that program, ITR program, may be considered as the one where NSF really put money on that direction, because that's a huge program. I still remember it was the year 2000. I was talking to the program manager, and the top of the bigger program. He said, you know, it's equal. The bigger programs coming up, NSF. It's a huge one. He said. Turned out it's a multi-billion-dollar for I think for like 5 to 10 years. I forgot it exactly now. So that really gave a lot of inspiration about the data and the genomic aspects of it. Then we also got a center to realize those kind of ideas with the industry. So then I got this MateriAlZ Incorporated company, which is my company in 2002. And then we, everyone knows that. Then we also formed the MateriAlZ Foundation 4 years ago, try to promote this kind of a computational based research and tools too. All right, so we talk about this building block materials, we talk about the experiments and modeling, we talk about spinning the bird and the cage. So we actually cover a lot of horizons. What do we do? Of course, we do experiments. So what are experiments then? Experiments actually are statistical sampling of multi-scale configurations. Like we talk about the bird in the cage, right? So you sample, if you sample very fast, you see the cage and the bird. If you sample very slow, you see bird in the cage. There are two experiments, okay? The experiments, say some different configurations or the mixture of configurations, okay? And then you try to figure out what are those configurations, right? Then you try to do some experiment, figure out the physics behind it. Now you see the bird in the cage is two configurations, the cage and the bird. And when the interaction is so fast, you see the bird in the cage. Okay, so you try to understand that observation. Then you do a model, right? You do a model. Modeling, you get model, you get feed parameters. Then you say, okay, you can, for example, that example, you can say, okay, how fast the spinning will give you the observation, the bird in the cage. Okay, so that's your model. You feed your model based on experiments, then you say, okay, now I'm going to predict it. Right? But you see, that's not really truly predictive because you have to have the observation as the input. And the truly prediction that the tool we have today is quantum mechanics, which is realized by density function theory. So that's truly predictive because it really does not require any observation you have. It does, of course, it itself has some approximations, but those approximations are not related to your observation. That's the key. It's independent. They are independent. And if you look at the quantum mechanics of density function theory, it really talks about the ground state. It says for any system, there'd be ground state at 0 Kelvin, and it has a unique electron density. Okay, that's basically what it means. Okay, but of course, we wanted to talk about at a different at a finite temperature. So then I talk about the different configurations, right, including the ground state. But most time we use very few configurations, and also we do statistical mechanics based on total energy. So we show that that's actually limitation of it. And yet, because it's so complex, so as scientists, engineers, we say, oh, maybe we should make it work. We need to do some approximations, like a hybrid a model, like effective Hamiltonian, then do MDMC simulations, the cross-grain the DFT, and the calified plus DFT. Okay, that's also the hybrid system. So you get some model, then you get some DFT, you put them together, and then do some predictions. So what Zentropy does, which I'm going to talk about today, is that we take the quantum mechanics, take statistical mechanics, okay? But the question is, it's here already, right? What's new? Okay, the first new thing is that you get a lot more states, okay? Not just a few states. You want to get all states, possible states, okay? How do you know all possible states? You just change all the internal degree freedoms. You sample all the possible internal degree freedoms. You then get the ergodic, we call it ergodic configurations. And then you can predict the free energy. That's important. DFT, we talk about 0 Kelvin, but DFT has capability to predict the free energy at finite temperatures for each configuration. Okay. And then put them back, use statistical mechanics. Now you see the difference here. The classical one uses total energy, but because it's very difficult, people go to this hybrid system. Okay, like a class expansion and a class variation method and so forth. But if we don't do that, the approximation, we take the DFT calculation, we take the free energy to the partition function, then we'll be able to predict the system without knowing what it may happen. So that's what the Zentropy is about. So again, we do not, before I did the bird and the cage experiment, now we do real experiment, real materials experiment, materials experiment. So the material experiment, we take the material that titanate. Okay, that is a ferroelectric material. We know that at low temperature, you measure it, you by X-ray measurements, you get the Ca ratio, right? So the tetragonal, and then the titanium atom moves away from the center, you get a polarization. Okay, so at the low temperature, tetragonal is ferroelectric, polarized tetragonal. All right, but if you increase temperature, it's still keep the measurement, right? Now your temperature goes up. What temperature goes up does is that the atom starts to move more, just like that bird in the cage, right? Traumatrope. So the atoms start to move more. Okay, they start interacting with each other more. Then what do you find? Do the measurement again. You find that the C ratio is decreasing. That means going this way, and the A axis is expanding, right? Okay, expanding. That's what you see. Then you see at the critical point, at one temperature, you find that C and A equal to each other. So you say, oh, now get a cubic now, right? Cubic. You also find that there is no polarization. It doesn't have any polarization anymore. It's zero polarization. Now you see, that's observation, just like it's a bird in the cage. You don't change the spin rate, but you increase temperature. So the question is that observation is correct or not, right? It's correct or not. So then now you start to experiment, right? So X-ray is a measurement, is one observation. Can we do different observation? Okay, now we have tools, we can do that. So we do a virtual experiment. We do the initial molecular dynamic simulation. So you get this one. So it takes cubic, right? It's cubic. It's cubic lattice. Okay, but this time it's not only one lattice, one nucleus, but multiple nuclei. Put them together because X-ray observation is scattering is as average. So average everything to be cubic. Okay, that's fixed. Then I look at each atom, titanium in the middle, and how it reacts with its oxygen and reacts with the lead. I can measure it, right? I can measure time. So what do you find? So high temperature first. High temperature. You see that the atom goes, the nucleus goes like this. Then after a while, it goes like that, or goes like this. So it changes the orientation of the C-axis. And if you decrease temperature, you find that if you decrease temperature, you find that it changes less frequent. Now that means that the high temperature changes very fast, but low temperature changes a little bit slower. Okay. So now it's with the X-ray, right? The X-ray. Now, if the X-ray is fast enough, you can see those changes. Then you say, oh, it's not tetragonal, cubic. But at high temperature so fast, you cannot see them anymore. It's the average effect, right? Then it's cubic. Okay, that's what happens. So that's black line, as I showed before. So you make the measurements, you got to see a ratio equal to 1 cubic. However, if you look at the individual atoms, individual titanium, you find that is most times tetragonal. That's the red one for the simulation just showed before. Then look at the literature. Turned out in 1994, people also measured it already. Use X-ray absorption fine structure, local structure observation. They find that the blue line is indeed the titanium is polarized, and you have C ratio all the time with the local ones. Even though overall it's cubic, but local nuclei they are all tetragonal with polarization too. You can also calculate titanium displacement. As again, it's you have the X-ray, we have this neutron, then we have the XF, we have the initial molecular dynamic simulation. So what does it mean? Just go back to the same thing as the cage, bird in the cage, right? So actually, even though you see the bird in the cage, but in the reality, because the two sides they flip each other so often, it makes you observe the bird in the cage. It's same thing here. So you actually have all the tetragonal, okay? But however, the tetragonal change so fast, when you look at them by X-ray, it's all cubic. But if you look at the individual titanium atoms, they're all tetragonal with polarization. So that's the picture. So both are correct, right? Both are correct. It's the scale, it's the resolution you have. Now, if you think about this one, if you want to predict the property of the cubic, you must know all those configurations are tetragonal. So you have to put the tetragonal and you have to predict the cubic. So that's really the message behind this one. Okay, that's what we came up with this Zentropy approach, how to do that. Okay, but of course, it's Zentropy is two words, is Z plus entropy. Z is a partition function in statistical mechanics is Zustadt-Summe in German, and it's sum of states basically. And then the entropy drive a change of system based on second law, and it's also out of statistical mechanics. Okay, so now you see two connection now, right? And then the entropy is basically let's count all possible entropies in a system, starting from electrons. Okay, then electrons is from quantum mechanics. So you take the quantum mechanics, put a statistical mechanics top of it, then you predict the total entropy. That's what entropy is about. Okay, and the entropy term, entropy term was suggested by postdoc in 2021 when he gave a talk like this. 2021 we had COVID, so I gave a talk. There some people, I don't know how many, 70 people at the symposium, at the seminar. They asked us questions. Then I was saying that we don't have the name for our approach. Josh said, "Oh, now you should call it Zentropy." Oh, we like it. So we call it Zentropy. We started using in our publication, but the work we started is 2002, 2008, like that. All right. So quickly go through the statistical mechanics, the partition function, probability of configurations, and it calculates energy, and it gets the entropy, okay, of the system. Now you see that this standard statistical use the EK, and then if you think about a system only with one configuration, for example, very, very low temperature, right? You have then F equal to EK. But also the F equal to EK minus TSK, that means SK equal to 0. That means all the configurations in this formula will have 0 entropy. That means they are pure quantum state. They only have one state, each of them. They can have two states. The energy can be different, but their state is only one. But when you talk about real materials, right? It's not. Real materials, you have a much more quantum states in one configuration. Okay, so that's why this equation is very difficult to use, okay? Because it's very hard to count all the pure quantum states. So what it means is that if you take a standard statistical mechanics, you calculate entropy. Okay, KB, PK log PK, that's the probability of each configuration. However, if each configuration also has its own entropy, then you have to add one term. You can go down continuously until you reach electron, right? Okay. Your upscale could be any scale you want, but you can decompose it and nested the formula, go all the way down to electrons. The reason you go to electrons is because you can use quantum mechanics. But if you talk about all individual electrons, then it's not going to work because there are too many of them to count for. That's why quantum mechanics was a theory, really not been very useful. Well, it's useful, but from the computation point of view, it's very hard until the density function theory comes into play, to be invented in 1960s. Okay, so summarize about Zentropy is really quantum mechanics plus statistical mechanics. Well, we believe that if you count all the entropy, the calculated one should equal to the experimental measurements. Experiment, you do not measure entropy directly, you measure the capacity to integration. Okay, that's what we learned from thermodynamics. Okay, and then the phenomena, we know that you could do the individual configuration, and also is configuration entropy among the different configurations. And you can start to predict. You can talk about the fluctuation of the configurations, disorder. You can talk about the anharmonicity. You can talk about the emerging microscopic properties, singularity. That's the most emerging you could get. The singularity, the system diverges. All right, so I have one slide to go through the density function theory. As I mentioned, quantum mechanics in the 1920s. 40 years later, Kang Xiang, actually Kang and his a paper in 1964 talk about the exact theory of many body systems. In 1965, they developed the exchange correlation functional to solve that equations, like to get an electron density of the state. And now the classical ones, you can do the ground state at 0 Kelvin. You can calculate the unique electron density, so it can give you the ground state. But when temperature goes to final temperature, you can talk about the thermal electronic contribution and the vibration contribution. Now you see that entropy is no longer 0, so it's not a pure quantum state. That means you cannot use the statistical mechanics before. And then if you talk about all other non-quantum states, and then each of them has a unique electron density, and then you sample all the degrees of freedom, and you can calculate the probably 0 Kelvin and find a temperature. Just use the method. Now you say you can get free energy for all kind of configurations, stable ones. If it's not stable, then you will not get the entropy, right? Because it should not define. It turns out the entropy can predict the unstable states. All right, so now let's look at the standard statistical mechanics. And we got this EK, right? F equal EK here. So this applies to pure quantum state, okay, with 0 entropy for each configuration. But if it is not, if each configuration has its own entropy, then we have to change it. We have to add the entropy of each configuration with a probability in front of it. Then we also get a free energy. We also have Fk instead of Ek, because each configuration has its own entropy. Then our partition function is always different. Instead of Ek, which is Fk, and then into the Pk. And we didn't know that before, but well, now we look in the literature. Actually, there are quite a few papers show this equation, but nobody used it. Nobody used it. We are probably the first one really use this equation to solve the problems. But that's very significant, because most of the people do is that you can calculate Fk, right? Then you do this hybrid model, as I mentioned before. They do Fk, they develop Hamiltonian for the system based on the Fk. Then you do the DMC simulation. In that case, you have another model procedure. Your data is not as accurate as the DFT itself before. So then you lose a lot of features of that one. And when Sk equals 0, then these two are identical. That also we like it very much, because if each configuration is a pure quantum state, then the original statistical mechanics is recovered. So that's give us a peace of mind that the approach we have is actually valid, is not in contradiction with the statistical mechanics. So I want to show one example about the iron 3 platinum. This one it has a negative sum expansion in some temperature range. So this plot shows the linear sum expansion coefficient of this compound at ambient pressure as function of temperature. The symbols are from 3 sets of experiments. Okay. Of course, you see, the experiment has uncertainty, right? Could it be due to the material's impurity? It could be because the measurement method, and a lot of errors could be introduced. But anyway, if you look compare these two, right? These two looks like more close to each other. And then you see that first is the linear sum expansion is coefficient is positive. That should be okay. Then reach a maximum, then start to decrease, then become negative. That means the volumes shrink when temperature goes up, and then it continues to be negative, then become the minimum, then starts to become less than negative, and become 0, become positive again. And this line is from prediction our model, our theory. We don't have a model here. That's very important. There's no model for us. Okay, we just calculate different configurations and they put it in statistical mechanics. So there's no model, no fitting parameters in this practice here. So how do we solve this iron 3 platinum? Iron 3 platinum is a L12 structure. So we take a supercell. Now, because DFT, you have the fixed supercell size, right? So we take 12 atoms, okay? 12 atoms. So 12 atoms, you have to be 3 linear cell. So you have 9 iron atoms. So you have 2 to the 9 power, give you 512 configurations. But some of them are the same because of symmetry. So we call it multiplicity of that configuration. But anyway, here shows the ferromagnetic state, all the spin goes one direction. Then you start to turn 1 spin, 2 spins, 3 spins, and 4 spins, and so forth, right? Turn all the spins in different direction. Then you got the different configurations. When you get different, as I mentioned, is 512, but only 37 are unique due to the symmetry. And then you can calculate their energy at 0 Kelvin. That's the first one. You see that ground state and the non-ground states. The important thing observation is that the non-ground states, they have smaller volume. That's very independent observation. And then you do the free energy calculation, right? Free energy calculation, calculate free energy as function of temperature at ambient pressure. And you find that the ground state is a difference. This ground state is always stable, has lowest energy. However, the difference between the different configurations decreases because divided by kBT. So the thermal energy makes them energy closer. Okay. And that means they're going to have a probability will be higher, right? So probably at 0 Kelvin is 100% probability for the ground state. Increase liberal temperature, still 100%. But if you increase temperature above like over 50 Kelvin, then the low energy configuration starts to show probability. It's not non-zero anymore. So probably here, the probability you see is all 100%. And then at this temperature range, this is normalized to the critical temperature 50-50 here. And you see the total non-ground state population increases. Having realized there's only one ground state, but there are hundreds of the non-ground state, right? So even though the energy is higher, but they overtake, they overwhelm the ground state. So ground state even becomes less than 15%. Okay, less than 15% at high temperature, even though the ground state has lowest energy. So now you see, from thermodynamic point of view, classical thermodynamic point of view, the ground state should be always stable. Nothing else should happen. However, from statistical thermodynamic point of view, and the ground state will decrease, the population will decrease to 50%. So we decided that if the ground state becomes less than 50%, that means when you do sampling of the system, you will not see that state anymore. Okay, you will see a mixture of everything. So that's where we decided that's where the system changed from ferromagnetic to paramagnetic. Even though the overall spin is 0, but it still have local spins. Then you calculate the magnetization as function of temperature, which is the overall spin. Okay, overall spin of 100% at 0 Kelvin, and then the percentage of the overall spin will decrease. It becomes 0 at a certain temperature. Okay, so that means we know that it's not exactly at this 50-50 because you have short range order in there, right? So you have some short range order in there above the transition temperature. Again, symbols are from experiments, and the line is from the prediction. Oh, it's pretty decent, right? Consider that we only have a 512 configurations, and we only have 12 atoms in our simulation cell. And we can phase diagram at different temperature and pressure, because you do different pressure now, right? You get an EV curve, you do different pressure. And you find that again, the temperature and pressure, this pressure is decreasing because minus P is our potential in thermodynamics. You see, again, the symbols are from experiments. Okay, lines from prediction. So above here is the second order transition. Below there is the first order. The first order seems to be much, some error, large error here. But the second order transition is beautifully predicted, including this critical point. So we can convert the pressure to its conjugate variable to volume. Then we got this phase diagram, temperature volume phase diagram. You see now give me speed gap. It's not because different compositions and different magnetic spin configurations. Again, each side has a mixture of different configurations, right? Different configurations. The interesting observation is that in this purple area, the different pressures in the purple area, that would have negative thermal expansion. So you see the band there, which give you negative thermal expansion. Okay. So again, this is really predicted with DFT calculations, putting in some statistical mechanics, and predict this transition. The only thing we have to assume is that when the transition takes place, we found that 50% is a good one. You can also heat capacity or magnetization and other quantities to compare, but we found this one is the most robust comparison. And here we show that. You can also talk about the curvature change, the degree of disorder. Okay, actually take different kind of disorder is actually pretty close. The predicted the inflection point. Okay, That's where the speed of change direction. First it's very fast and becomes slower. Okay, so you can do different kind of the study the sampling, so to speak, and get different data there. But it's very close. So the latest one we did is nickel. It's called strongly correlated materials from the solid state physics. It's very similar, right? So again, here you have nickel. It's magnetic. Yttrium is not. Oxygen is not. But this unit is much bigger. It's 80 atoms. Remember, equivalent to 12 atoms, right? This is 80 atoms. So it's very difficult. Turns out the nature plays a dice again. Is that the sum of the nickel has no spin, a very small spin. Okay, so that makes calculation much simpler. You can remove half of the calculations, right? Half of the calculation you don't need to do. Again, we do the energy at 0 Kelvin. Now you see this is very different than before, right? Before the metastable one goes this way. This was almost like doesn't change. Okay, almost doesn't change. So it doesn't cost each other much. And then you can do the free energy calculation, the same approach. Now you do this again, this comparison. There's the population probability, 100% antiferromagnetic state, that's ground state. Then the populations of the decrease and reach 50%, I take 50%. So the cross 15% is 144 Kelvin. The experiment, I'm going to show next slide, is 145 Kelvin. Again, there's no approximate, no feeding parameters here. But however, if we take the standard statistical mechanics, that means take the total energy in the partition function of the configurations, we get 81 Kelvin. Okay, that just shows the importance of use F K instead of EK in the calculation. Okay, so that means that well, I think that's why we were trying to call ourselves approach statistical mechanics. It confuses with people. So we took the suggestion from Josh to use called Zentropy. Zentropy basically means that just standard statistical mechanics take the EK and the Zentropy approach take FK in the calculation. And then you can calculate the PT phase diagram. You can see the big difference from the FK and EK calculation. Again, experiment 145 Kelvin, and there's no other experiments yet. We can do more experiments for the function pressure. I know the ASU and I just built a very large high pressure experiment, and also I know that the University of Arizona also has this geoscientists with the high pressure. So we can do the high pressure prediction. We can also do short range ordering now. Try to figure out short range ordering, the local ones, right? And how that changes. All right, so I go back to the Latin I started before. So Penn State it's one of the leading university, at least in the world, about ferroelectrics. Okay, so I always wanted to do this one, but I haven't figured out how to do that. I did not figure out until a couple of years ago. I got a visiting scholar. Then we finished that 2015 PIB paper on the AMD simulation. Then I realized that we did different configurations, right? We need to figure out the configuration. We have the ground tetragonal polarized one and the cubic one, okay? But the cubic one is not really the configuration behind it, because behind it are all the tetragonal polarized configuration. Then realize that, okay, when the spin change, right? You have all spin up first, polarization. If you want change, turn this way, you get 90-degree domain war. This is this one, right? And then if the spin turns that way, you get 180-degree domain war. It turned out, of course, that has been studied extensively in the ferroelectric community. And in 2002, the first paper used DFT, calculated the domain war energy for the 190, 180, and 90-degree domain wars. Then we said, okay, if we take this three configurations, right? We take the tetragonal without domain war, that's our ground state. Then we take the two states, two map configurations. One is 180 domain wars, another one is 90 domain wars. Then we take the data from the literature, the energy. So people calculate the 90 degree has 35 millijoule, and 180 is 132. Of course, there are couple of configurations that people have proved that in the literature that they have very high energy. Then it's very high energy, probability is 0, right? Even 132, 180 degree domain was also almost 0 probability. Very, very low, because you have 35 and 0, right? The another one 0, going to say 0. So this 2 has dominance. So to the same approach, we calculated, this time we didn't get an entropy yet, okay? We did get entropy. And turned out the prediction is not bad. It's just 13 degrees off from the experiments. This gives 2 indications. One is that this given the configuration have probably very similar entropy. Okay, so it doesn't affect the probability if you add entropy. Secondly, if we add entropy, that's what we can work on, they maybe give you almost an exact prediction. Okay, so that's what we're working on now. But anyway, you think with this one, right? Take this partition function, so the main thing here is to get the configurations for us to understand it. Then take the data from the literature and predict transition. Now you think about that one, that the two-sided bird in the cage, somersault. Now you have three sides, right? Now you see you have the three sides the dice. Okay, now you flip them. You actually have 2 because this one's almost 0. So you have 2 sides. One is the tetragonal polarized, another one is 90 degree. If you flip them enough, you get a cubic structure. Okay. Of course, the 90 degree domain has 4 configurations. So it's 4 to 1. Okay, it's 4 90 degree domain wall configurations. They have multiplicity, and the quantity is 1. 180 degrees is also 1. Okay, that's one of the reasons. And 90, not only 2 reasons, right? One is low energy, and other one is the 4 multiplicity. This one. So you have to have you think you have a 4 dice, 4 sides of the dice. Okay, 5. A 390 degree domain was 490 degree domain was 1 ferroelectric going state. Now, if you spin that slice at high temperature, you'll be able to see the transition to cubic at 776 Kelvin. All right. So to do that, we need a lot of tools. Okay, so we give a lot of tools to do that. We call it the ocean of data. Is data and the tool to combine together. So you first have the general data. Okay, you have to do the free energy, not only 0K, right? Free energy. So we developed a code called the DFTTK, which is do the free energy calculation for any configuration. And we know the free energy calculation is DFT takes time, so we also have a machine learning code. But this one's only for 0 Kelvin at the moment. We're going to do some people at NIST developing the one for the entropy. We're going to implement that one. And then we compare experiment data, right? We want to compare with the experiment data. And always use experiment data. And we're developing one called Zentropy to put what we talk about today in the software, which Dr. Yuan, Professor Yuan at Penn State is working on, focus on that one. After you got all the data, you need to compile them in the databases. Okay, where PACAF and SBA to combine the database, we're going to do multi-component system. If we don't do multi-component system, that will be sufficient for just one compound, right? For lead titanate, we don't need this one. This is sufficient. However, if you want to do the lead titanate in another lead oxide, titanium oxide, right? Then you need to have a database talk about multi-component, multi-phases. And then we also do this a short course on training, and we have a new program to start to make it into the community code people can use. Do I have 3 minutes? Is that do I have 4 minutes? Krishna?
We have plenty of time.
Yeah, definitely.
Okay, so I do want to go a little bit. I know that most grad students here, I want to talk a little bit more entropy, actually general about thermodynamics. So I talk about quantum mechanics. I talk about the statistical mechanics, right? But we also have we also talk about the classical thermodynamics. Okay, so I want to make those connections. I want to connect the classical thermodynamics, the quantum, to statistical, and even to the irreversible thermodynamics. So this will be to be learned from thermodynamics, canonical cycle. We got for a closed equilibrium system, we got the entropy change definition. If you open the system, you add heat, you add the mass, then you get the mass entropy contribution. If the system is not in equilibrium, you get another one, entropy reduction due to internal process. So this equation covers equilibrium, open system, non-equilibrium. So I call the open non-equilibrium system. to the entropy change. But of course, this is only change, but we really want to get entropy itself, right? Then we have statistical mechanics, okay? That's what we know this equation, they call Boltzmann entropy. And then actually this equation is a special case of the Gibbs entropy with the probability. If each configuration has same probability, it gives us the Boltzmann equation. Okay. So in principle, we should use this one as I demonstrated today. We should not use this one because most of the time, the different configurations have different probabilities. Now, quantum mechanics give us a very critical importance as I showed today, right? If I don't use that one, my prediction is way off from experiments. That's one of the reasons I believe why the quantum mechanics from experiment point of view, people say, oh, your prediction is not good. It doesn't agree with my experiments. Okay, because quantum mechanics, most of them predict one to a few configurations, or most of the ground state configurations. But we have different ones. So for different configurations, we can calculate their free energy. Okay, the phonon, of course, you can do E minus TS, you get the electron contribution. Okay, so you put them together, now you get quantum mechanics here, right? So I have statistical quantum mechanics. That's where I should agree with experiments as we demonstrated. Okay, demonstrated. So now the question is that where do we go from there? So we got thermodynamics I showed before. That's our thermodynamics, right? And then we got our function here. So if most of I would think it's almost all textbooks focus on the first terms. Okay, last term is dropped. Why is it dropped? Because it was dropped by Gibbs in 1870s. Because he was focused on equilibrium system. When equilibrium system, this one equals 0. Okay, so that's called classical thermodynamics. When this equals 0. However, when this equals 0, does not mean that equilibrium. That's very important. It is equilibrium, there's no driving force for the internal process, but it could be frozen into. So that's the non-ground states. It's metastable. You have a fixed configuration of internal configurations. That internal configuration is not an equilibrium configuration, but it's frozen in either by your theory, right, the DFK, or by experiment because the diffusion is so slow, nucleation is so slow. So classical thermodynamics actually already involved non-equilibrium. It's for the frozen in configurations. Okay. And then we talk about the quantum mechanics. It really calculates the SK and FK, not only EK. That's very important. Okay. And then we put a statistical mechanics, is put this entropy has two parts. There's a standard statistical mechanics, and there's the extra from the quantum mechanics. So this formula includes the quantum contributions. Okay. So that's beauty. Now I think, in my opinion, it's really the first time we put a complete quantum mechanics into the framework of thermodynamics through the statistical mechanics. So statistical mechanics is not the end because you need to still get the free energy to calculate it, right? So what the irreversible thermodynamics is the last term is not equal to 0. Okay, is not equal to 0. So that means something is happening there. Okay. Okay. Of course, if it's not equal to 0, that means D is not equal to 0, D psi is not equal to 0, right? Now, both of them 0. Then you get irreversible thermodynamics process. So how to do that? Okay, so that's what our latest work is on the direction that basically you have a final relation, right? How do you calculate D psi change? Okay, when a D psi change is flux, right? It's flux. Okay, it's flux. So you can do the entropy production. There is a flux. Okay, you can actually configure, you can actually examine it and see how it works. Okay, it's entropy production rate. Then you can do the volume change. You can do A times delta Z distance. Now you get the distance into it. You get the time and distance into thermodynamics. Then you get a flux and the driving force. Okay. So you get a flux driving force. That's the important definition. The flux of one molar quantity, volume, whatever you have, is the ratio change of that molar quantity. That molar quantity must be proportional. This must be proportional to the driving force. The driving force is a conjugate variable. That's very important. Okay, but in the literature, oh, I have the next slide maybe. Maybe should be here. I didn't put it here. Okay. Anyway, and then you can do the calculation of the entropy production. It's always positive. That's also that's the process taking place. Okay, it's very different from Onsaga formula. I know that some of you are doing this work. our second formula says that J, the flux of one component, for example, the species, is proportional to all driving forces, all potentials in the system. Okay, which if you're interested, I have in this paper, I discussed why this equation is incorrect. This equation is phenomenological. Okay, it derives phenomenology. Phenomenology, why is that? It means if you change the temperature, you can get diffusion, right? That's right. Temperature does drive diffusion, but not in this equation format. Okay, that's what they derived it, called the theory of cross phenomena. Cross phenomena is that, again, this flux equation. Okay, then it's important to realize that the molar quantity, this is xj, is solely driven by its conjugated potential gradient. X and y, they're conjugated variables in the combined law. So where does cross phenomena come in them? It's because the potential gradient of this variable is function of all other potentials. So if there is a gradient of this one, you can decompose it into different variables in its own molar quantity gradient. That's a composition, for example. If the chemical potential, this is a concentration gradient. But if you take this term only as fixed law, so fixed law is inaccurate. Okay, fixed law is inaccurate. I really think we should not teach fixed law in our class anymore, because you have other contributions there. Okay, another composition, for example, then temperature gradient, the electric field gradient, electric field or magnetic field, right? Or is a stress like a peer and we were discussing before the seminar here. So this is what because this phenomenon, this observation temperature can drive diffusion, for example. It's not because you need the temperature gradient here, it's because the chemical potential is a function of temperature. All right, so we have a lot of examples here. All the examples we have in the literature, some electric, some diffusion, electromigration, electrocaloric, electromechanics, this is ferroelectric stuff, and uphill diffusion. For example, we talk about uphill diffusion by Dakin, and it turned out that if you use fixed law, it's not working. Okay, but if you use this formula, it's going to work. Okay. And we do have examples showing the Seebeck coefficient. Again, Seebeck coefficient in the literature is always a kinetic coefficient, but we demonstrated that is the derivative of the is the second derivative of the free energy. I'm sure that some people will not agree with me, but I hope them to look at our paper and see if they can be convinced. If it's not, we can set up a meeting to discuss. And this is the properties. This is the first derivative of the potential to a molar quantity. Give us all these physical properties: some expansion, paraelectric coefficients, paramagnetic coefficients, piezoelectric moduli, and piezoelectricity. All those are the second derivative of the free energy to a molar quantity. Okay. We'll talk about this cross phenomenon. There's another set of derivatives is between two potentials. That one is very rarely discussed in literature. For example, I mentioned if it's electron, chemical electron potential to temperature derivative, that gives you Seebeck coefficient. Okay, so these are the new quantities we think it should have a large impact on what talk about the properties of materials and also for material design purpose. All right, for that one, I'm going to summarize. Talk about the Zentropy theory. It counts the total entropy of a system by combining quantum mechanics and statistical mechanics. You can go from start from electrons going all the way to whatever scale you have. So it's a nested formula. Second one is the predictive. Okay, it only has a approximation from DFT, and then you need to figure out all the configurations. Like again, start from the ground state. You can predict the properties which you think is abnormal, like the negative sum expansion. Temperature is not abnormal, and it's not actually not part of bonding too. Okay, it's not actually part of bonding. People think that negative sum expansion, your bonding should go to zero, right? Or you go negative. Okay, your force go negative. No, force doesn't go negative. That's just that's just like a bird in the cage. Bird is not in the cage. It's your observation shows the bird in the cage. But in reality, bird is never in the cage. And then it enables integration of the classical thermodynamics, quantum statistics, and irreversible thermodynamics. You can put them together now because we can get the fully consideration of the entropy, because entropy drives everything. And now I hope you are convinced. You agree with me now. Previously, at the beginning 20 years ago, I think the individual phases are the building blocks. Now I think the configurations are the building blocks. They're part of the different configuration put together to form a phase. The phase probably can be abnormal, but the configurations themselves are normal. You only put them together, you get nonlinear interaction through the entropy term. That's a logarithmic term. Okay, so we're now trying to apply it to different phenomena. This is a new project we're just starting. If you go to this web page, you will see that. And we want to use the entropy theory to predict the transformative functionalities for a range of materials. Again, we're also open for collaborations. If you have since you would like to work with us together, we'd be love to work with you. To end it, I want to show that there's two papers, which the recent paper we have 2020 and 2022, and which is summarizes most of the approaches we have. Thank you very much.
Thanks a lot, Professor Liu. I think we can open up the floor for some questions. Anyone? There are some few hands that were raised.
Hi, Zikui.
Uh,
Great talk. Fortunately, this is the third time I hear this talk over the past few months, so that's helped me understand. And frankly, every time I learn new things. So today I just realized, because you told me you and your students are calculating melting temperature, and liquids has just so many configurations, right? So I think I have an approach to sample just a few and make it simple. But I'll discuss it with you in the afternoon.
That'd be nice. We can write a paper together now.
Yeah, great.
So I have maybe it's almost an ignorant question, but in your Zentropy, I mean, in the models that you presented, has the role of vibrational entropy been taken into account fully? I mean, because in some sense, right, if this vibrational part is in some sense you're accounting for the different degrees of vibrational freedom and weighing it with respect to the temperature according to Bose-Einstein statistics. So is that something that's inherently taken into account, or is there somehow the additional entropy term that you're accounting for is taking into account the compensating for the vibrational entropy part?
That's actually a great point. We have not solved that problem yet. And our vibration approach calculation is for individual configurations, right? You get 100 configurations, calculate all the vibrational property. And then we do this Zentropy approach. Then we got the total entropy.
Yeah.
But we cannot go back to get the final density of states yet. We cannot resolve back. See what happens there.
Okay.
That's our problem now. Okay. So we're trying to figure that out, but we have no solutions yet. And even you actually even want to go further back even more. You wanted to go back to even get the photon spectrum, right? Can we put the photon spectrum of a mixture of the configurations?
Yes, that's what. Yes.
We can even go back and say, can we predict the electronic spectrum of the mixed states? Well, that I think is Qijun. If you can get that problem solved, that'd be fantastic.
Krishna, I have a question.
Yeah, Ankit.
Yeah, so my question is very much also in line of what Krishna asked. I was originally going to ask you about the vibrational, but my question now is slightly different. So the configurational part of the entropy, say if it has 2 or 3 different configurations, so isn't the classical entropy already kind of having the averaged entropy of state? And then if it is really supposed to be distinguished as 1, 2, and 3, shouldn't this be a weighted mean so as to how much time the system actually spends in each of these distinct states?
Yeah, that's exactly the question we had at the beginning.
Yes.
Actually, that's quick. People ask us, did you double count the entropy? Right? That's the question. Is the entropy double counted? Okay. So then we went back Wilson is not double counted because you can think about it, if you start, that's why our connection to the standard statistic is important. Okay, suppose you have a pure quantum state, right? So now I have entropy because there's only one state. Okay, of course the total energy changes a function of temperature, but the configuration is only one, always one, because pure quantum state. So in that case, you see zero contribution from each configuration to the total entropy, except the pk log pk.
Yeah.
Okay, so now you think about, okay, if one of the configuration has some entropy, how do you count that gets into the system? That is not in that anymore. It's not in your pk log pk. So you have to add on top of it. Then each configuration has its probability. So it's only part of his entropy is contributed to the total entropy. That's the pksk summation to that part.
Okay.
So it was we didn't actually we couldn't answer the question at the beginning. We didn't know. Then when we figure out the pure quantum state, then you find a G. It's not double counting anymore because you can go to state without entropy. You have no contribution there.
Right. So VK, if there's just a follow-up question on this. So if, say, for example, we suspect a system stays for a greater time, let's say we have some count of time and it stays for a larger time in say configuration 1 and spends lesser time in configuration 2. So that's where we start blurring off the difference between a metastable and a stable state, right? So I'm really talking about that line. So shouldn't this be accounted for? Because if a system is less likely to,
yeah, it's kind of let me finish your question. Sorry.
Yeah. So if the system is less likely to spend time in a given state based on the probability, then it should have less contribution in an entropy.
Yeah, it's just well, with less or not, it may be not fully clear. Okay, because you can, for example, you can fix temperature, so you can have a entropy change outside with surroundings, right? So the system entropy may increase or decrease. We don't know that. Okay, could it decrease?
Yeah.
Could decrease. Okay, you actually did a very critical point, which is that's why the last part, irreversible sometimes works for us. Okay, we can predict unstable state.
Mm-hmm.
You see, that's the key. That's really important because you think this one, you have metastable, stable, right? You can suppose two configurations. Right. Of course, each of the mixture of configurations, right? But then you have to go from metastable to stable, right?
Yeah. We
can predict that barrier completely without any fitting parameter. Actually, yesterday was a question when I gave a talk. Somebody asked a question, say we have some trouble for graphite and diamond, okay? And I didn't realize that when we do this kind of sampling, we don't take the equilibrium energy as our summation. We take it at any fixed condition as our summation. Yeah. So you can predict the maximum, you can predict the inflection point, you can put everything you have in the system. And it's a very beautiful thing, which is because people ask this type of question. And the beautiful thing is that with all the configuration being stable, because that means no imaginary phonon, you can predict instability of a system. That's beautiful.
Yeah. All right. Yeah. Thank you.
I have a question. And Professor Liu, we're meeting after this, so we can continue the conversation later too, as well. I work a lot in nanotechnology, where size-dependent properties exist, surfaces become very important, surface energies, and is there a systematic way or an approach where we can, include some of those effects into what you're doing?
Yeah, I think
it's a very broad question. You can choose to answer in any direction, please.
Yeah, I think it's possible. The reason because
I think your student is doing it, B-Chen.
That's good. See, that's good. That's good. Yeah,
I'd love to talk about that.
The idea is really that you need to figure out the configurations. Okay. Now the challenge you have, the one challenge is that when the surface to the interior, you have continuous change, right? Continuous change. The case I talk about is the whole system homogeneous, right? When have this location specific mixture. So that's the only thing I think is difference. You have the location. That means you take the location as subsystems you have. Then you add them together for your system. So you have to divide your inhomogeneous system to homogeneous system in the global scale. Okay, because in our case it's local inhomogeneous, global homogeneous, right? But in your case it's global inhomogeneous. Okay, so you have to take. So that means you have to divide your global into subsystems and solve them individually because each of them has different constraints. Solve them individually, then put them back. I think you will get the nano behavior, in my opinion. I hope that's what the business is doing, but that's what I was thinking should be done.
Thank you. Thank you. Appreciate it.
I think, Professor Liu, would it be okay if like some of the audience reach out to you and email you because some of them were going to watch it after the recording? Is that something okay with you?
Yeah, that's perfect. Okay.
Okay. I think this was a very, very informative and completely new way for, at least from a material science perspective, of thinking of thermodynamics of materials. And hopefully this gives rise to many more collaborations between the Arizona universities and Penn State on these ideas. So if there aren't any other questions from the students, I think we should probably call it a day. And once again, let's thank Professor Liu for a great talk. Hopefully this is one among the many new ideas that come from Professor Liu's group on these stuff. So with that, I'll first stop the recording if I can, and then
Yeah.